Next, we have Yuan Liu from NC State. They will present his work together with Victor Albert from UMD, who's currently not here. But he will present the RQS seed grant related to phase space formulations and simulation of molecular conical intersections.
You hear me well? Good morning, everyone.
Yeah, good.
How about now?
Captioning is on.
Yes.
Okay. You hear me well? Great. All right, good morning, everyone. My name is Yuan, and I'm a faculty at NC State. Today, I'm going to give updates about some of the work we have been doing with my graduate student, Aline Das, who is here, and also Victor Albert from Maryland. And I guess some of you probably already seen Aline's poster last night, but I'm going to give more background and slightly more future outlook on some of the connections to other fields. You might notice the title is a little bit different from the agenda. The agenda was supposed to kind of see how a phase-space formulation will help us actually simulate conical intersections. But we realized that actually the phase-space formulation itself already have quite some interesting things. So I'm going to focus a little bit on this motivation and some of the results on the phase-space formulation itself. And then I will mention some connections to conical intersection. This is still ongoing work. So 2 questions for motivation. Why molecules? So you can think of that molecule as a really complex quantum systems that sometimes is classical, sometimes quantum. And you would think that given so many, quantum degree of freedom in a very compact space location, obviously, it's probably really good for quantum information processing. For example, I'm giving here this really complex energy level diagram called the Jablonski diagram, which says that in molecules, you're going to have some electronic states, which is given by the dark solid bar. And every electronic state have spin angular momentum. For example, here I have 3 singlet states, S0, S1, S2, and then 1 triplet state over there on the most right-hand side. And then every electron state supports lots of vibrations, and that's the sort of thin lines above the solid dark line. And then every vibration yet supports lots of rotations. That's the small lines above the vibrations, right? So you see, this is super complex. And then once you give one initial excitation, there's going to be lots of couplings, inter-system crossings, all that complex things happens. You would think this is really good, but then in the end, it also brings lots of trouble and difficulties in controlling and actually leverage this, right? So one of the interesting things that people was doing originally is doing spectroscopy. First of all, you might want to just probe the energy level diagrams and see where they are and what's the transition between them. And that actually usually give you good energy and momentum information. For example, this is something called photoelectron spectroscopy, where you just heat your molecule with lasers and you knock out electrons. You're going to detect electrons' momentum, energy. You can infer, what's the vibrational states. Each one of the peak here represent, small one vibrations. But we also have lots of different experimental advancement. For example, the ultra-fast technique can allow us to actually see how reactions happen in real time in locations. You can actually use X-ray scattering to see how actually in a ring opening reaction of this small molecule, what's the position information. So the energy, the momentum, the position, this experimental probe across different time scale and energy scale give you a really complete phase space description of molecules. But then we still wanted to have a theoretical understanding, back to that complex things, and can we actually see some useful structures? Can we leverage those structures to speed up simulation or design new codes, right? So this is the sort of motivation. And of course, many of you know that in the center, Victor and his co-authors have this beautiful paper on figuring out a quantum theory of molecular orientations, where they actually show that if you consider the rotation, rigid body rotation of a molecule coupled to the nuclei spin, and you can actually find interesting entangled joint symmetry adapted bases in any molecules. And what they were able to show is that on the leftmost side, they can construct this phase space, so-called eigenstate of the position of the molecules by forming a generalized sort of Fourier transform from the momentum states, which is the familiar sort of angular momentum state that you would know. And then they give lots of interesting sort of constructions and examples showing how actually this enables new kind of symmetry, the coupling between the nuclei spin and the point group symmetries. But if you think, a little bit more, right, so you realize that lots of degrees of freedom are not present in this construction. For example, what about vibrations? What about nuclei spatial? And those are also quantized degrees of freedom. So one of the main questions we ask here is that, can we actually incorporate the nuclei spatial and vibration, and even electronic spin and spatial all together into this unified phase space description? And then the second question is, of course, what is it good for, right? And so let's kind of think a little bit detail about this. What do you get? So we have electronic spin spatial, right? Nuclei spin spatial, and the rigid body rotation and some translation as well. And what we wanted to do, the phase space formulation, really wanted to think about the generic sort of theory that is mostly Hamiltonian independent. So you do not want to find a molecule that say you solve the many-body Schrodinger equations of all the degrees of freedom, right? So that's sort of, very hard, first of all, and you might not have a good way of solving that. And, you lack some theoretical understanding in the first place. And we want to work, this works for a broad class of molecules, right? So what is really the structure in generic molecular systems? And really, right, so there's the symmetry. The shape is a point group that you get. And there's all these spins that has the angular momentum couplings, which is described by some angular momentum theory. And really, right, so for generic molecules, it seems like this is pretty much what you can get. So if we think about, in this way, right, so one of the first things we know is that symmetry adapted basis is good in all the molecular phase space. If you can find a symmetry adapted basis across all the degrees of freedom, then naturally your Hamiltonian will be block diagonal, and you will be able to actually find some interesting, separate some interesting degrees of freedom from the other. And then you can look at individual symmetry sectors itself. So if you think about the generic sort of symmetry of the molecule, of course, it's going to be the symmetry of the nuclei and the rotation product. The symmetry of the electronic has the spin and the spatial part. And in the rest of my talk, I'm going to try to just to say electron spatial is usually, sort of high energy excitations. It doesn't change that much. I'm going to ignore electron spatial for now, but I can mention that in the later. And electronic spin, which is the same sort of angular momentum coupling that was treated in Victor Albert's paper by rotation sort of spins. So that treatment also, so we can do that later. But I'm going to focus on the first part, that first gamma there. How do you actually couple the vibration, the spatial part of the nuclei motion, so to establish the eigenstate of the rotation and the spin of the nuclei, which is what the previous Victor's work did. And this will give us actually an entangled basis, as I'm representing the second line of parenthesis there. And of course, the spatial, the rotation and the spin of a nuclei part, again, the third line can be decomposed as some entangled basis that's already built, established in the prior work. So our main goal here is actually to focus on the second line here in the parenthesis and really study what's the symmetry of the vibrations, spatial vibrations of the generic point group symmetry molecules. I give you a molecule, right? So there are three N atoms. Well, I can find 3 N minus 6 in general vibrational degrees of freedom, and then you can say each vibrational degrees of freedom actually is labeled by the point group irrab. Okay, and you can actually figure out how many modes, vibrational modes, belong to each irrab. That's fine. But the tricky thing is that actually every vibration could have many Fock level excitations. And that you can go to in principle, infinitely high, but of course, at some point, the normal modes vibration approximation breaks down. But what happens if you actually have high Fock level excitations? How does the symmetry of your vibration change, right? And that's obviously one key question. So it turns out that if you only have one-dimensional irrab, the symmetry of your overtime, I'm going to call this high-level Fock level excitation, just going to be alternating between the symmetry of the mode itself and the all-symmetric symmetry. Right? So it's just like even, if you have even excitation, you're going to go back to the all-symmetric irrab. If you have odd excitation, the symmetry of the state itself is the symmetry of the mode. Okay? And the tricky thing is the high-dimensional irrab. And this actually happens a lot in high-symmetric molecules. For example, methane, which is TD symmetry, right? And they actually got some three-dimensional degenerate irrabs. And if you actually excite some high quantas overtones in that mode, what's going to happen? So it turns out that there is some established spectroscopy techniques that chemical physics actually work this out. For example, in a two-dimensional case, if you have VI, excitation, VI overtone Fock level excitation in that E mode, E is a 2D mode, it turns out that the overall symmetry of the state is a mixture from different symmetry sectors, including A1, which is a totally symmetric one-dimensional irrab, and then E itself. And then it has A2, which is a one-dimensional irrab, but have some minus sign under some reflections. And P and Qs are some integers related to VI. So basically, give any excitations, you can sort of figure out what is the symmetry of that overtone. But this is good, but it makes a symmetry, right? So if you think you wanted to construct some pure symmetric global sort of symmetry of adapted state, you might want to kind of separate the symmetry from each other. So how can you then construct a pure symmetry vibrational wave function on this degenerate high-dimensional irrab modes, right? So because all of these coefficients are known, it turns out they can just take linear combinations of all different overtones on that same high-dimensional mode. And what you can get actually is this purely symmetry vibrational wave function for each mode. So let me kind of try to explain this a little bit more. Whatever I'm showing on the left here is some examples for some non-abelian group, point group C, D3 and T and O, where there is some two-dimensional irrabs, okay? So that's E. But once I put high overtones in E, I'm going to try to generate lots of mixture symmetries. But if I actually linear combine different Fock level excitations altogether, the line there, first line there, it's basically saying I can combine, let's say 1, 2, 3, 4, 5, 5 and 6 different things, even more, to get a totally A1 symmetric wave function from this overtongue excitation. And you can actually do this for like A2 and E as well. And all of that, the coefficients is sort of dependent on the overtongue n that you have on the mode. And so those are all can be worked out. And for some other groups, depending on even or odd, for example, D4 and S4, you're going to have slightly different construction, but the general idea is sort of the same. So I'll give you one example here. So this is a boron trifluoride molecule, which got a sort of D3 point group. Okay, so it has a threefold rotation in the plane. It's a planar molecule, and then you have 3 reflection group actions, and also this in-plane sort of reflection. And it got, you can count, right? 3 times 4 minus 6 roughly give you 6 vibrational mode. And then that's the, one of them has E1 symmetry, one of them have A2, and then you got a pair of V3 that has E erap, and another pair that has the E erap as well. And you can sort of turn on the cranks we discussed before and figure out the wave function of each one of the symmetries of the mode. And then you can form some linear combination of the joint symmetry across all the vibration, rotation, and nuclei spin. Okay, so this long basis I'm writing down here. Let me explain this a bit more. The first, the cat. So this is the Fock excitation on the mode A1, okay? And whatever you have there, it's always going to be A1 symmetry. And the second cat here is the Fock excitation on A2. And if you keep that as even, you're going to have A1 symmetry, okay? My goal here is to construct a global A1 symmetry wave function across all the degrees of freedom. And then the third here, the 2E mode, and then we already know how to get a A1 symmetry out of the E excitation. And then you can just pick some, point group A1 symmetry from the rotation and nuclei spin. And you can see that this basis, right, the entire symmetry is still A1 because every one of them is individual A1. So I just multiply them and I get A1. But then there's also some other second term there where you let 2A2 appear, and then you're gonna, get still global A1 symmetry. And you can keep doing this, and you can find all possible sort of ways of generating the same sort of A1 symmetry. And then you can do the same thing for sort of A2 and global E symmetry, right? So this sort of gives you a unified symmetry adapted basis across the nuclei vibrations and combined with established rotation and nuclei spins. So why is this useful? One of the things is this. If you think about the natural dynamics in molecules, given some dynamical excitation, let's say, in electronics, oftentimes the dynamics go across different degrees of freedom, from electronic to vibration and then to rotation, and lots of dissipation and conversion happens. There's this thing called conical intersection where, Duke and Ken's group here has really nice work on this. There is even statistical arguments saying there are actually so many conical intersections in molecules, right? So one of the things you might want to do is that when you think about simulating this dynamics, when you are far from a conical intersection, actually usually the nuclei is classical. You might want to have classical treatment. But when your dynamics is close to the conical intersection, nuclei become really quantum. And to have a scalable, efficient simulation, you might want to detect in the algorithm where does that happen. And how do you detect that? You can think when kind of this coupling, really strongly coupling happens, you're going to have entanglement between your electron and the vibration and the rotations. So the basis set we designed are sort of all entangled bases that has the same sort of global symmetry. And because the dynamics, the molecule, right, the Hamiltonian sort of obey that symmetry. So all the dynamics in principle will happen within the same sort of global symmetry sector. But it's possible that they're going to just shift between different degrees of freedom within that symmetry sector. And then you're going to produce a highly entangled state. So if you can actually do some basis measurement under this symmetry adapted entangled basis, you might actually be able to detect. And this is just some idea we're sort of still thinking more about. And then the other idea is that now you know how to leverage the symmetries in a broader molecular phase space. Can we actually design broader class of code based on this, beyond the rotation code that Victor worked out before, and actually combine the symmetries, right, the spatial information of the molecule vibrations. So the third thing is that, if you kind of try to generalize this symmetry a little bit more, right, so what's all the possible symmetries in molecules? Then you can kind of figure out lots of different things, and can we actually, leverage all of this symmetries? We started doing this by figuring out some, quantum algorithms that can leverage symmetric groups, permutations between identical particles, and then do some simple things in the past year. So just to summarize, the conclusion is that we developed sort of a unified theory for molecular phase space, and then in particular incorporate the nuclei sort of spatial vibrations. And then there is a symmetry adapted molecular basis that you can develop based on this point group symmetry and some characters. But there is more work, as I mentioned, that's being done. And again, I wanted to acknowledge the collaborators and the seed grant support. I would just say that my group also works on two other directions. One of them is thinking about hybrid continuous discrete variable quantum computing. And the other is the broader quantum engineering field of, thinking how quantum can change the classical field of electrical engineering. And that's it. And happy to take any questions. Thanks.
Maybe one quick question.
May I ask, so is there any understanding of what is the main error mechanism from the understanding of this molecular phase space, maybe from the physical chemistry?
Yeah, so I think those probably going to come from experiment probes. What's the main error mechanism? So there are all sorts of different couplings between different degrees of freedom. If you think that you isolate one part of the system, you can oftentimes figure out the couplings, and then you will say, okay, that's going to be your error mechanism. And then the other way is, of course, you probe experimentally what's happening.